cloud, and then as soon as you know, maybe at like 12:30 or something like that, I'll get an email that says, hey, your Zoom meeting's done recording. And I'll be able to post the link to it like I did here. And then the format is like, I should have made the subject of this intro video for Acceleration Lab and discussion question, because then down here, that's the only discussion question you ever have to do. It's the one that's mentioned in the in this announcement for every, like for instance, like this one, and this one, and there'll be another one where it just tells you what the discussion question is. And that's in contrast to whatever it says in the assignment. The assignments are kind of locked in. So I don't change those. I just change what's required here. So let's head over to the, no, not that, the lab manual first. So we'll open up our Google Sheets. And what else will we need? Lots of Logger Pro, but we can also open up our uncertainty. We'll need that at some point, and open up the plotting tool because we'll need that at some point. Okay. First thing to mention, as always, there's this new thing this year in all the data sheets that I don't understand. So feel free to just ignore this entire box right here. My computer isn't highlighting it. There we go. I'm just gonna get rid of it. And then a kind of a annoying organization thing. These boxes right here, the GHIJ rows 2 through 5, you can Command X to cut that and put it down here, because it actually is incredibly confusing because people were thinking, okay, I do this, 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 and this, and then I get the slopes, which is not the case. You need to get this data in this box. You need to get this data in this box, and then you're plotting this column versus this column. We'll get to that in a second. It's just some organizational things, and I'll explain further in a little bit. Okay, back here. So firstly, what is the physics of what we're doing today? So these two equations should probably be familiar from, like, maybe they were on your midterm formula sheet or something like that. They are two of the equations for kinematics. One of them is in the x direction, and one of them is in the y direction. The first thing we're going to do is analyze in the y direction by thinking about physically what's happening in our lab today. So we have like these setups. Yeah. It's in the Blackboard notes. So it should say like extra office hours, and it has like a Zoom link. It has like a Zoom.com .j a bunch of numbers. J is like, I think it stands for like Jason's meeting room or something like that. So in terms of like what is physically happening throughout the lab today, we have some ball that's rolling down a track, and then it's going to fall off the table. And the parts of the equation that we're looking at right here, this y equals h 1/2 gt squared. The height is like the initial height of the desk. So that's how high the desk is. However, the y coordinate of the ball is not always at the height. So right now at t equals 0, y equals h. But once y equals 0, the ball is on the ground. So y equals 0 is ball on the ground, y equals h is at its initial position. So what we're going to do is take one of the limiting cases, which is as soon as the ball hits the ground, and we're going to plug it into this equation. And what that's going to do is we're going to look at the whole time that the process takes. So for instance, from the top of the desk to the bottom of the desk happens when y is equal to 0. And so we plug in 0 to the left-hand side of this equation. We have the height here, the 1/2 gt. So this is like the distance change due to an acceleration acting on it. And we rearrange this equation, bring the h to the left-hand side, cross out the minuses. I bring this 2 from the denominator up into the other side, and I divide by g. And then I take a square root, and now I'm left with this formula, which tells me that the time it takes for the ball to leave the ramp and hit the ground is the square root of 2, the height of the desk, over gravity. Next, now that I know that, I can ask what's happening during that time. Like, not only was I dropping the ball straight down, but because the ramp launched it off, it had a velocity in the x direction. So now I know how long it takes to get from desk to floor, which is irrelevant, or doesn't take into consideration the velocity. It's if I drop the ball or if I throw the ball this way, it's going to take the same time for it to fall on the ground. The only difference is it's going to travel some horizontal distance if it has a initial velocity, which it does. And so that's where we use this equation. Another way to think of this x is range. So for instance, the range with which the ball travels from the edge of the desk into the classroom. So everyone will be like shooting the balls this way. And it looks like we do have enough lab desks. So yesterday, the people in the middle in these 2 tables, because you guys don't have a ramp, you had to go to the classroom next door. But it looks like you should be fine in order to use an extra, because it looks like we have 2 people without partners, so you guys can team up, and then you guys can have a whole 2 lab stations. Anyway, so the objective of lab today is to measure how far the ball travels, and then we get x. We're going to figure out how fast it's traveling using Logger Pro. I'll get to that in a second. And then we're going to, like we did last time, confirm that the acceleration due to gravity is 9.8 meters per second squared. So how do we do that? Now we can plug in the time it takes to fall to this equation. Range equals the velocity times the time it takes to fall. And then we can kind of analyze what we're doing here. So first, let me just show you this picture here. This is like exactly what we're doing. So up at the top of the desk, we have our little ramp and we have our ball. The desk is some height h above the ground, and the ball travels out with some velocity vx. And on the ground, roughly, this really isn't to scale. The piece of papers that are on your desk will be like laying flat. I'll do a little demo really quick. And definitely, if this is what your paper looks like on your desk, just come up here and get a new one, because it's hard to keep track of all the dots. So you get a blank piece of paper, and this can be beat up, it doesn't matter. And you place the piece of carbon paper over the paper, and you lay it some distance away from the table. And then you take your ball, and you let it fall onto the paper. And then this carbon paper will have shot some carbon onto the white paper. And so now you can measure from this thing called the plumb bob, which is like a piece of string and a paper clip or a nail or something. This gives you just an idea of the straight down. Like this is hanging straight. Well, this one isn't because the nail's touching the ground. But most of your nails or paper clips or something aren't touching the ground. And so that thing called the plumb bob it gives you kind of an origin. So you're measuring from the plumb bob to wherever that black dot on the paper occurred. And so by doing this is what we measure by hand. We measure the range. So this is this x variable. The next thing we do is we know h, we know 2, and our objective in lab is to find g. So if you can anticipate what we're going to do, we're going to do a y equals mx plus b graph as usual, but we're not there yet. So how do we find this v, this velocity that the ball leaves the thing with? Because all we're doing is putting it on a ramp and letting it go. So how do we know how fast the ball is moving? Next, we have to kind of, in many ways, it uses, at least like you can think about it mentally as the answer to the discussion question that we did last week, with like the how does the Logger Pro actually work? The answer was really that it's kind of just a glorified stopwatch. The Logger Pro starts measuring something when it's being blocked. So for instance, it's not measuring anything now, the light is off. Nothing is blocking the laser that comes out of here and is absorbed by this photodiode or whatever it's called. But as soon as I put my finger in front of the laser, it starts measuring its time. So now the light is on. And as soon as I take my finger away, it stops measuring. So it's really just a stopwatch that's accurate based on sight. So like if it can be seen through or not. And so what we're going to be doing today is using that concept and this weird device that we have to get the velocity. So what we're going to do is kind of measure the diameter of the ball, or rather how much of the ball passes through, like if you can envision this as your laser, how much of the ball passes past the laser. And we're going to call that our distance, or the diameter of the ball. You can also think of it as like the diameter, even though it may very well be that that much is passing through. So like your laser is doing this. That's not bad. It's just that you have to be consistent about it. So if this is your diameter, we can measure from Logger Pro on the computer how long it takes, because the light will turn on here. Imagine my ball is going this way through the thing. The light will turn on as soon as it hits this edge of the ball, and it will turn off as soon as it hits this edge of the ball. And so we're going to use the diameter of the ball, the time that we get from Logger Pro, which is like, it'll give you a time. So it'll be time 1, time 2, and then we can subtract those two. So delta t in our Google Sheet will be time 1 minus time 2. And then we can use the velocity as distance over time. So distance here is the diameter of the ball, and delta t is how long the laser was blocked. And so how do we get this diameter of the ball? That's the annoying part of lab, because in theory, what you can do is you can just put it up to kind of like a ruler, or you can use a micrometer, like those things that you kind of like clasp onto it and you can read from it. However, the diameter like that I mentioned, it may not actually be this. That would be ideal if your laser is set up exactly so that the middle of the ball passes through your thing, because that's more or less something that you can reliably guess on. However, it may be the case that it's here. This is fine, but that's why we're doing what we're doing, and which is we're going to use the crank on this machine. So if you look towards the wall on your on the device, but the edge of the device closest to the wall, there's this little knob. And it turns out that if this is the knob and this is your ramp. So this perspective right here is drawn like, because I was sitting over here when I drew this picture. So this is over here is this little knob. You can either spin it with your finger, or you can crank it like I don't know, some kind of, drawbridge on a castle or something. And as you spin that thing, what you'll notice is that the photo gate is moving forward and back. Let me just bring this down here. So, as I spin this thing, which may not even be on camera, I can't even tell. Let's click that, like that, and yes, now I can see if it's on camera. Okay, so as we spin this thing, what you'll be able to see, it's very slow, but you can, with your eye, you'll be able to see that this thing is moving. So this is the photo gate, and what we're going to do is we're going to move this thing back. We're going to place the ball so that it rests right here. And we're going to spin the photo gate, or spin this wheel until the photo gate is blank. Because if the photo gate is blank, that means it's not measuring the ball yet. The ball is still not there. So like that, that's kind of, I unplugged it so I can bring it over here so you won't see the light turn on. But anyway, what I'll be doing is I will start spinning my little wheel. And as soon as the light turns on, I'm gonna take note of where this thing is. So for instance, now I'm going to start looking at this, and it's going to be kind of like my reference point. So let's say the light turned on as soon as I got to this point. What I'm going to do next is I'm going to consider this like x equals 0 for the origin. And the next thing I'm going to do is start counting. So if this is the origin, that means I'm going to keep spinning so that the photo gate continues to pass over the ball. So for instance, the photo gate would be moving this way, like outwards until it passes over the whole ball. And I'm going to keep spinning, but I'm going to count. So if this is my origin, 1, 2, 3, 4, and so on, until I get roughly the number. I gave you kind of an example of what I found. It was roughly like 20 to 25 turns. But the tricky part is that it won't exactly, it would be very weird if it fell exactly on some number. So some number in it, like an integer, like 1, 2, 3, 4. What usually happens is you get to you're like 22, 23, and then the light turns off and you're like, your knob is like over here. And so what you have to do is come up with some way to define what that is. Like what fraction of a number is that? So if this was 0, I'm going to say this is probably like a quarter. And so what I would write down is 23 and a quarter turns until the ball came off. And you can add some uncertainty. You can say it was, a quarter. You can tell the difference between, but maybe an eighth, like that and that you can't tell the difference between. So you can use an eighth of a turn as your uncertainty, or a quarter of a turn. And then what we're going to do, this is kind of like the small d from last class. Now we have some kind of conversion on all your things that says 1 millimeter per turn. And so now we know how many turns it takes for this thing to go past the ball. And using that conversion, now that we know how many turns, this thing is called the screw pitch. That's what's written or etched on all your devices. It's 1 millimeter per turn. We cancel the units, so 23.5 turns times 1 millimeter over turn. The turns cancel, and I get that the diameter of my ball is 23.5 millimeters. One thing to keep in mind for later in the lab, when you're measuring ranges and the height of the desk, most people use centimeters because it's a more convenient thing. Like the range of the ball will be like that or something. And most people, if they see that, they say 17.5 centimeters. They don't say 175 millimeters. So you have to use the same units for everything. So it doesn't matter if you use millimeters or centimeters or meters, but you have to stay consistent throughout the whole lab. So if you want to measure the height from the desk and your range in centimeters, which I think is a good idea, it makes more sense, convert this value to centimeters. So for instance, this is 23.5 millimeters or 2.35 centimeters. So that just keeps things consistent. And now from Logger Pro, as soon as you press collect and you drop the ball, you will get a time start, like a T1 and a T2. And what you do is you say equals T1 minus T2, and you get some value. This is an actual value, so I'm just kind of giving you guys some rough estimates. And then the velocity will be, and here I kept things in millimeters. You can do that. You can do that if you like, but I didn't. Which is you take the distance of the ball or the diameter of the ball, you divide it by that delta t, and you get the velocity of the ball. Now that we have the velocity of the ball, we can return to our equation over here. We have this, we measured it from the floor. We just got this from Logger Pro. And now we can start to use our kind of the thing that we use all the time, like the y equals mx plus b. So now we plot the range, how far the ball traveled on the ground. On the y-axis, we plot the velocity on the x-axis. And in doing so, as a result, this quantity now becomes our slope. And so once we do our plotting tool with range on the y-axis and dx on the x-axis, we get that the slope is equal to this. And then what I can do is I can rearrange this formula. So I square both sides, so it's the slope squared. For some reason, they call the slope t. It's a little confusing to me. I mean, I get it because this quantity is actually the time down that we found. I just think it's kind of confusing for them to do that. Why can I not see? I'm trying to figure out how to get back to. You can't move the. Oh, there it is. So yeah, I guess that the slope actually is equal to the time it takes to fall. It's just an extra piece of difficulty that I don't think is necessary. So you can just call your slope t. Anyway, if the slope is t and it equals this thing, if we want to solve for the acceleration due to gravity, what we do is we square both sides. So it would be t squared equals 2h over g. And then we flip these two things because we can multiply by g so that it would be t squared times g equals 2h. And then we divide by t squared so that you end up with this thing, where t is just your slope. And so that's the whole procedure of the lab. Let me see what these other two slides are. Yes, after you have measured the diameter of your ball with the turning of the thing, in general, as you can see, I just mixed up playing with this thing. This isn't very, and this isn't particularly straight. So what you can do is unscrew these kind of tighteners here, and you can make it straight. But once you do this, and once you measure the diameter of your ball, you have things straight. For the whole rest of the lab, try not to touch all this. Because what you'll do, if you do, for instance, if you do that later by accident, what you'll be doing is you'll effectively be measuring, maybe when you calculated the diameter of the ball, you were doing this. But if you touch it, you'll be doing that, which is a different distance. And so if you touch it later in the lab, you may have to go back. And one way you can test that is at the very end of lab, you can do it again. And if you get the same diameter of the ball, that confirms you didn't touch anything. But obviously you only have to do that if your value of G is like way off or something. That would be a way that you could say, oh, this is why my data is bad for this lab or something. Another thing that hopefully makes things easier for you today, throughout in the lab manual and from the Google Sheet, you'll be able to see that it asks you to do the point on the ramp, lowest, second lowest, middle, highest. What that means is taking the paperclip. It means taking the paperclip and moving it to different heights. And the reason you do this is because you want to have you want to reduce error. So for instance, you don't want to say, okay, I'm releasing it from here. And then you do it and you do another trial. Okay, I'm releasing it from here, which is supposedly the same point. What you do to make sure it is the same point is you clip this thing to the ramp. And now you say, okay, when I'm doing trial 1, 2, and 3 at the lowest height, I release it from here. So it's kind of like a limit on how high you can put the ball. And then you drop it from here and put it off. They want you to do 5 different heights. So like 1, 2, 3, 4, 5. I think that's way too much, especially because there are a lot of people here and there'll be balls like shooting on the floor. And now that like there are like a full class, like only one of you guys can go here, and then the other will have to go in the 119, which is right next door, which is like where we are on solar. The door is open. Just check. But anyway, you only have to do 3. So do like this will be your lowest. This can be your middle, and this could be your highest. So what effectively that means is you can just do this for your Google Sheet. Oops, that's not what I wanted. And just block out 2 of the trials. It's doing 3 different heights and getting 3 trials for each of them, so 9 data points is way more than enough. 15 is overkill, and it will take forever to do 15 of them. That's all I have. Let's see, I don't think there are any other slides. One more, the uncertainty. This is actually kind of irrelevant. When I was doing this lab, I didn't realize that they, not only do they have a column for the slope, but they also ask you to do the slope squared and do the height over the slope squared. Basically what they're doing is they're breaking up this equation into like 3 steps. So instead of like, remember when I did the trapezoid uncertainty and I did like 3 steps in one, that's basically what I'm doing in that slide. Just because I think it's easy to do it that way because things end up simplifying. But what they do here and on the Google Sheet is they break it up. So like, for instance, once you have the slope, you use equation 11 for this because that's the squared. And then once you have the squared and some quantity h, then it's equation 11 because you have an a over b. And then once you go here, this is just in order to get from this to this, right? That's just a 2. And so you'd use equation 7 because 2 is a constant. So it just makes it easier for you to do the uncertainty. So you really don't need this picture right here. Anyway, okay, that is it. I will end the recording and it'll eventually get to you. Stop sharing, stop recording.